Hi everybody, I hope this video finds you well. In today's video, we're going to be moving on with our discussion of the chi-squared hypothesis test, but we'll be changing gears and moving on from the chi-squared test for independence and homogeneity and introducing a new chi-squared test, which is called the chi-squared test for goodness of fit. We're going to introduce this hypothesis test, and we'll see that it has a few differences from the test for independence and homogeneity, but most of the computational moments are very similar, and then we'll get into an example of actually running this test. So this will be the chi-squared test for goodness of fit, and this is again a global hypothesis test, meaning that this is a hypothesis test that is used to diagnose sort of a global change or a global difference, but it doesn't necessarily tell you what that difference or what that change actually was. So this global hypothesis test is used when you want to determine if the distribution of a categorical variable is different or has changed from what we previously assumed or knew about that distribution. So once again, this chi-square test is related to a categorical variable, but it's not about the relationship between two categorical variables. It's actually about how a single categorical variable is distributed. And what we mean by distributed is basically the percentages that we expect to fall into each category of that categorical variable. One quick note with this is that to run this chi-squared goodness of fit, in general, the categorical variable that we're talking about should have at least 3 categories. So sort of a tip-off for identifying a chi-squared test for goodness of fit is you see a single categorical variable with 3 or more categories. And if you see that and you see a discussion about its distribution, that's a good tip-off that it is a chi-squared test for goodness of fit. All right, so what do the hypotheses look like here? Well, unlike the chi-square test for independence and homogeneity, where we wrote out the hypotheses as sentences, this time we are a little bit more mathematical. The null hypothesis for a chi-squared goodness of fit is going to be what percentages or proportions we think fall into each of the categories. So it'll be P1 equals something, and we'll have to find the value there. P2 will have to be equal to something. P3 will be equal to something, so on and so forth. Now, I put this ... here because we know that it has at least 3 categories, but there may be more than 3 categories. And in your null, you will need to say what percentage we assumed or knew, or previously knew, was supposed to fall into each category. The alternate then is that at least one of these proportions has changed or is different than we previously assumed. Now, we could be a little bit more specific here. Since this is a distribution, these proportions all need to add up to exactly 1 or exactly 100%, which means that if one of them changes, actually at least another one has to change. If you think about it, if one goes up by 5%, some combination of other ones has to go down by 5% to balance everything back out to 100%. So we could phrase this as at least 2 of the proportions has changed, or at least 2 of the proportions are different. But we don't really bother with that because that just sort of is an awkward phrasing, so we just say at least 1. But just keep in the back of your mind, actually if one changes, at least another one has to change as well. Notice that also in this alternate hypothesis, this relates to what we meant by a global hypothesis test. We don't say which of the proportions has changed. We don't say if some have gone up or some have gone down. We're just saying that some are different than we previously thought. So this is, again, what makes it a global hypothesis test. All right, so that means for the null, you will be filling in some values for what percentage you thought or what proportion you thought landed in each category. And then the alternate is always going to be the same for these goodness of fit. At least one of the proportions has changed or is different. Just like the chi-square test for independence and homogeneity, there is an intermediate step that we will do after we set the hypotheses. It's going to be constructing an expected counts table, just like before, but the way we do it is a little bit different. It doesn't make sense to do row total times column total and all that stuff because we don't have a two-way table. So instead, what we do is we take for each of the values in the null hypothesis, we calculate the expected count by doing the expected count is the sample size times the proportion. In other words, the expected count is basically saying what percentage or proportion do we think landed in that category and how many people or individuals did we have in our sample overall. Multiply those together and that'll give you how many people or individuals you expected to be in that category. So that's how we'll construct those expected counts table, and we'll do this formula for each of the different categories or each of the different proportions we have. The conditions then are going to be exactly the same for chi-squared independence and homogeneity and this chi-squared goodness of fit. So the sample must be random and representative, sample size must be less than 5% of the population size, and once again, we're going to need to look at all the expected counts we build, and we need less than 20% of those expected counts to be smaller than 5. So we can't have too many really small expected counts. For the test statistic, it is exactly the same formula, so we will be calculating that chi-square test statistic, and it'll be the sum of the differences between the observed and expected counts squared divided by those expected counts. And again, what is that measuring? Well, it's basically saying how different is what we observed versus what we expected relative to what we expected. The p-value then is going to be again calculated using table D because this is a chi-squared test statistic. Once again, to go on to table D, you do need a degrees of freedom. And the degrees of freedom here is once again based on how many options your variable has. So the degrees of freedom here will be the number of categories minus 1. So we simply look at how many categories we had, subtract 1, and that'll give us our degrees of freedom. Step 5, always the same, the conclusion. If the p-value is less than alpha, we will be rejecting HO, which means we have evidence for our claim, meaning that we have evidence that the distribution has changed or is different. If the p-value is greater than alpha, we will be failing to reject HO, which means that we have no evidence for HA, which in this case means we have no evidence that the distribution has changed or is different than we originally thought. So, once again, this is a pretty similar test to independence and homogeneity, but the main point here is that it really is used for a different thing. Independence and homogeneity is used when you want to test if there's a relationship between two different variables. In this goodness of fit, you're testing whether or not the distribution has changed. So you're looking at a single variable and you're trying to figure out if the distribution has changed. Okay, so let's go ahead and get into our example here. So for our example, we want to study if the distribution of car colors in the US has changed since 2000. So to do this, we find a study from 2000 that gave us the following distribution for car colors. So the study from 2000 said that 11% of cars were black, 21% were silver or gray, 17% were white, 5% were brown, 11% were red, 9% were blue, and 26% were some other color than the ones listed here. So, to see if this distribution has changed, what we do is we randomly select 150 cars from across the US and we record their colors. So we get the following data here. There are 31 black vehicles, 41 silver or gray vehicles, 37 white, 6 brown, 15 red, 12 blue, and 8 that were some other color than the ones listed here. So what do we want to do in this example? Well, we're going to carry out at alpha equals 0.05 a hypothesis test to test the claim that the distribution of car colors in the US has changed since 2000. Notice that we have that sort of key word here. They were talking about the distribution of car colors. As soon as we see that, that's going to be our tip-off that this is going to be a chi-squared goodness of it. It's talking about the distribution of car colors. And then we're going to build a 99% confidence interval for the percentage of cars in the US that are black, silver or gray, or white. All right, so let's get right into this and talk about how we're going to do this. So for A, like we said, this is going to be a chi-squared goodness of fit. And again, the big tip-off here is the fact that it says distribution. As soon as we see that mention of distribution, that tells us that it's going to be a chi-squared goodness of fit. All right, so the first thing that we need to do then is we need to set up some hypotheses. So for our hypotheses here, we need to come up with our null and our alternate. Now we know that our null in this case is going to be whatever the percentages or proportions we originally assumed. So if we look back, we have this study from 2000, which is what we're sort of working off of. If that's what's true in 2000, we're going to sort of work from the assumption that that's maybe still true. And then of course our claim against that, our alternate, is that it has changed. So we will be using this as our null hypothesis. And notice that makes sense because it's a list of percentages. So we can just make a little note here. This is going to be our null hypothesis. So let's go ahead and write that out. We can do P1, P2, P3, meaning like this one would be 1, this one would be 2, this one would be 3. But it might also just be easier to use some subscripts to make it a little bit clearer. So piece black here, right? Again, we can write it as 11%, but it's probably easier to write it as a decimal since we are going to have to do some computations with it. so we'll say 0.11. Then piece of silver and gray, that would be 0.21. Piece of white, which would be 0.17. Piece of brown, which would be 0.05, because that's 5%. Piece of red, which would be 0.11. Piece of blue, which is 0.09. And piece of other, which is 0.26. One other quick thing, how do we know that this is a valid distribution? Well, if you want, you can just check by adding these percentages up. 11 and 21, that's 32. Plus 17, that's 49. Plus 5, that's 54. Then 65, then 74, then 100. So this really is a valid distribution, 100% there. All right, what's our alternate? Well, the alternate, for goodness if it is always the same, we're going to say at least one of these proportions, or you could say percentages if you prefer, at least one of these proportions has changed since 2000. And notice that I would probably use the language of has changed rather than is different, because we're talking about from 2000, from the year 2000 till now, so 20 years later. So we're talking has changed is probably a better terminology there. All right, now that we got that, we can go ahead and do our expected counts table. So this is our intermediate step. So remember that our formula is going to be our expected counts are going to be n times p sub I. And we're going to do that for each of these. So what we're going to do is we're going to recreate this table of data, but according to what we expected based on these hypotheses. So let's go ahead and see that. So for black, right, how many black vehicles were we expecting? Well, our sample size was 150, and we expected, according to this original null, 0.11 or 11% to be black. So let's go ahead and check that. That would be 150 is our n, and the proportion for black was 0.11. So we do 150 times 0.11. And if we go ahead and do that, 150 times 0.11, we can see that the expectation here is going to be 16.5. So that's what we were expecting to see in terms of the amount of black vehicles. Now, the other ones, I'm not going to write out the formula, but we can calculate these as well. So for silver and gray, well, what are we going to be doing here? Well, it's still going to be 150 is our n, but the p is going to be 0.21. So we'll be doing 150 times 0.21, and we should get 31.5. Then for white, again, the n is going to be 150. The n is never going to change because that's our sample size, but the proportion is, it's going to be 0.17 now, so 150 times 0.17. So that's going to be 25.5. And then for brown, it's going to be 150 times that 0.05, so 150 times 0.05, so we get 7.5 there. For red, it's going to be, again, 150 times 0.11, so 150 times 0.11, it's going to be 16.5. For blue, we're going to take 150 times 0.09, so 150 times 0.09, 13.5. And finally, for the other, which will just slide down a little bit, it'll be that 0.26, or sorry, that 150 times that 0.26. So 150 times 0.26, looks like we should get 39. Now, what do we think we would get if we added up 16.5, 31.5, 25.5, 7.5, 16.5, 13.5, and 39? Well, if you add these guys up, and you can check this on your calculator, you will get exactly 150. Because what was our sample size? It was 150. And we're saying if things are exactly the same as it was in the year 2000, this is how those 150 vehicles that we looked at should have been distributed, according to this information here. Here's how they were actually distributed. This is our actual data. And this test will be comparing how different this is from this expectation here. So there's our expected counts table. All right, let's go ahead then and check our conditions. So we'll be on step 2 here. We've got our conditions. So first one, random and representative, that was stated in there. So we're all good with that. 2, we need to have our sample size be less than 5% of our population size. Obviously, we can just say that there's lots of cars or vehicles in US, so we're definitely good there. And then finally, our third one is less than 20% of the expected counts coming in smaller than 5. So let's see. We had 16.5, 31.5, 21, 25.5, 7.5, 16.5, 13.5, and 39. None of those came in less than 5. So we had 0 out of, I guess we did 1, 2, 3, 4, 5, 6, 7 different expected counts. So 0 out of 7 is 0%, which is definitely less than 20%. So we're all good. Could we have gotten away if one of them had been less than 5? Maybe this brown, if it had come out as like 4.5 or 3.5. Well, if you check on your calculator, 1 out of 7 is about 14%, which would be less than 20%, so we'd still be okay. Now, if 2 of these guys had come out less than 5, then it would be 2 out of 7. That would be like about 28%, and then we would fail this condition 3, and we would be stuck there. But in this case, we're all good. All right, let's go ahead then. And since we've got everything on this page, let's go ahead and try to squeeze in the test statistic here. So for our test statistic, remember we're going to be using that formula of chi-squared is the sum of the observed counts minus the expected counts squared over the expected counts. Now, of course, we know that the expected counts are right here. Where are the observed counts? Well, observed counts are always your data. It's the one thing we haven't used here, which is that big list. So these will be our observed counts. What our actual data show. That's what we observed. That's our observed counts. So our first computation is that we observed 31 black cars versus an expectation of 16.5. So the first part of this test statistic will be 31 minus 16.5 squared over 16.5. Then plus the next one, which is that we observed 41 silver and gray versus an expectation of 31.5. So we'd have plus 41 minus 31.5 squared over 31.5. Then next thing we observed is we observed 37 white cars versus an expectation of 25.5. So we'd have plus 37 minus 25.5 squared over 25.5. Then plus, and next one is we observed 6 brown cars versus an expectation of 7.5. So that would be 6 minus 7.5 squared over 7.5. Plus, then we observed 15 red versus an expectation of 16.5. So 15 minus 16.5 squared over 16.5. Plus, then we observed 12 blue versus an expectation of 13.5. 12 minus 13.5 squared over 13.5. Finally, plus last one, we observed 8 other colored vehicles versus an expectation of 39. So 8 minus 39 squared divided by 39. So there we go. Because we had 7 categories here, we have 7 components to our test statistic. Now to actually compute that, we'll go ahead and we'll move that onto our next page now that we have that all written out. Okay. We'll just copy that. All right, we'll give ourselves another page to sort of work on here. All right, so there's where we were at. Okay, let's go ahead and actually calculate this then. Remember, when you guys are doing this, you don't need to write all this out, but you do need to write out what each component gives us. So the first one, 31 minus 16.5 squared divided by 16.5. That gives us a contributing test statistic of 12.74. Plus 41 minus 31.5 squared divided by 31.5. That gives us a 2.87. 37 minus 25.5 squared divided by 25.5. Looks like plus 5.19. Then plus 6 minus 7.5 squared divided by 7.5. 0.3 plus 15 minus 16.5 squared divided by 16.5. Looks like 0.14 plus 12 minus 13.5 squared divided by 13.5. Looks like 0.17. and then 8 minus 39 squared divided by 39 looks like gives us 24.64. So now we can go ahead and sum these together. 12.74 plus 2.87 plus 5.19 plus 0.3 plus 0.14 plus 0.17 plus 24.64. Looks like we should get a chi-squared of 46.05. Again, remember, if you guys were doing like a T or a Z test and you got like 46.05, there's probably a computation here, but these chi-squared test statistics can sometimes turn out to be a lot larger, so this looks all good here. All right, let's go ahead and get our p-value. So we'll need to jump onto table D, and we'll need to know our degrees of freedom. What is our degrees of freedoms? Well, it's our number of categories minus 1. So let's go take a look. How many categories do we have here? Well, we had 1, 2, 3, 4, 5, 6, 7. We filed every vehicle into one of 7 categories. So we had 7 categories here. 7 minus 1 equals 6. So we have degrees of freedom 6, and we have a chi-squared of 46.05. So let's go find that on table D. There we go. There's chi-squared of 6, and we are looking for 46.05. So 46.05 looks like it takes us off the table there on the right-hand side. Yep, looks like we are right there. So remember, these p-values, they get smaller as you go to the right. So we know our p-value is incredibly small. It is smaller than 0.0005. So we just figured out here that our p-value is less than 0.0005. Very, very small here. All right, we're ready then to make our conclusion. And our conclusion, if we take our p-value, which is really, really small, less than 0.0005, that is certainly less than 0.05. So we are comfortable with the conclusion of reject HO, which means we did successfully find evidence. So we'd say significant evidence. That looks ugly, so there we go. Significant evidence that... Well, what was our claim? If we look back, our claim was that at least one of these proportions has changed since 2000. Or, if you prefer to say it more sort of in a consolidated form there, right? You can say that the claim was that the distribution of car colors has changed. So, either way would be appropriate, but we do have evidence for that claim. So, significant evidence that the distribution of car colors has changed since 2000 in the U.S. So, in other words, we are convinced that the distribution of car colors in the U.S. has shifted since 2000. Do we know exactly what that shift has been? No, right? We would have to do more analysis, but remember, if we look back here, this hints at where the biggest changes occurred. Obviously, the biggest one was this last one, which came from the other category. Let's see what happened there, right? Well, in the other category, remember, we were expecting to see 39 vehicles be other colors rather than the 6 we had listed. We only had 8. So one of the things we might investigate for how car colors have changed over time is that other car colors, things that are not black, silver gray, white, brown, red, or blue, have really decreased in popularity since 2000. What other were large contributing test statistics? Well, probably the other really large one was that first one, 12.74. Even that one's only half of this. So this is really probably where the majority of the relationship is, or more the majority of the change is. But this 12.74 is also pretty large, so let's see about that. That came from having in the sort of black category, right, that we expected to see 16.5 black vehicles, but we saw 31. That means that maybe another part of how this distribution has changed is that vehicles that are black have become a lot more popular over time since the year 2000. So those would be the types of things we would investigate if we were going to do further analysis here. So this is your guys' first example of seeing a chi-squared goodness of fit test. Now, we did have one more thing we wanted to do. We wanted to build a confidence interval. So let's go ahead and do that as well. Let's give ourselves one more page to do that. So for part B here, we wanted to do a 99% confidence interval for the percentage of cars that are black, silver/gray, or white. So sort of these 3 main colors, we'd like to know what percentage of all cars do those three main colors make up there? So what type of interval is this going to be? Well, it's a 99% confidence interval for a single percentage, not the difference in percentage, but just a single percentage. So this is going to be a one sample proportion confidence interval. All right, so we've got some conditions to check here. The first two conditions will have already been checked, so 1 and 2 already checked. That makes sense because the first two conditions are just the ones about the data being random and representative and the sample size being less than 5% of the population. But 3 is the one about successes and failures. So we need to know our successes and we need to know our failures. Now, what counts as a success here? Well, 3 things count as a success: black, silver or gray, or white. Any cars that were those 3 colors are successes. Anything else were failures. So let's go back and look at our data. So remember, we're not going to be looking at this. We're going to just be looking at the observed counts, our data. So we had 31 black, 41 silver and gray, and 37 white. Putting those together, we had 31 plus 41 plus 37, 109 successes. So our successes here would be 109. That is greater than or equal to 10. We're all good. For our failures, we have 2 ways we could figure that out. We could remember that our sample size was 150. 150 minus 109, which is 41, would give us the number of failures. Or we can just go back and count everything that wasn't black, silver, gray, or white. So let's just go confirm. We had 6 brown, 15 red, that's 21, 12 blue, that's 33, 8 other, that's 41. So, yep, we did have 41 failures here. And that is greater than or equal to 10, so we're all good. Then we can go ahead and do our construction. So remember, our formula is going to be p hat plus or minus z star square root p hat 1 minus p hat over n. So we need 3 things here: p hat, n, and z star. How do we find sample proportions? Number of successes divided by sample size. We should remember that our sample size is 150, and our sample proportion then should be 109 out of 150. 109 divided by 150 should give us a sample proportion of approximately 0.727. So about 72.7% of vehicles in our sample were black, silver, gray, or white. Now we're going to try to do that as an estimate for the percentage of all cars that are those colors. What about our Z star? Well, it might have been a little while since we did one with 99%. So remember, you could look at table C, go down to the Z star row. Confidence level here would be 99%. Let's go ahead and grab that on table C. So there's 99% right there. There's Z star right there. Looks like it should be 2.576. Notice a lot of times we've been doing this, it's been 1.960 because we had 95% as our confidence level. This time we have 99% though, so we got to alter our Z star. 2.576 here. So we got 2.576, and we can go ahead and plug that in. All right, let's go ahead and do that. So we got 0.727 plus or minus 2.576 square root 0.727, 1 minus 0.727 divided by 150. All right, now we can go ahead and do the margin of error, 2.576. times the square root, 0.727, times 1 minus 0.727, divided by 150. And it looks like our margin of error there, we should get 0.727 plus or minus 0.094. All right, then we can build our interval, 0.727 minus 0.094, and we can get 0.633 plus or minus 0.727 plus 0.094. Looks like we should get, sorry, not plus or minus there, comma, 0.821. Then we can interpret that. We can say we're 99% confident that between 63.3% and 82.1% of cars in the U.S. are black, silver or gray, or white. So in other words, we're saying anywhere from about 63% all the way up to about 82% of the vehicles out there in the U.S. are either black, silver, gray, or white. All right, so there we go. There was doing a sort of follow-up confidence interval based on our data. Again, remember when we introduced this new chi-squared stuff, we didn't introduce any new confidence intervals, so we're still just using the old confidence intervals that we worked with. Since everything's been categorical here, all the confidence intervals we've been using as follow-ups have either been 1 sample proportion or 2 sample proportion. In our next video, we'll do one more example of the chi-squared goodness of fit test, just to make sure that we're comfortable not only with the computation, but also with setting up the hypotheses, because we'll sort of see a special situation where the percentages for the null hypothesis aren't immediately given to us. So we'll see that in our next video.